Hello, my name is BSnow, and I'll be talking today about how I've used image correlation to understand electrical chatter. I'd first like to thank Carl and Kathy, my mentors from Sandia, and the sponsorship of the Texas A&M Online OREU program. So why should we study electrical chatter? When we want two electrical devices to communicate with each other, we often connect them physically using an HDMI port or a USB plug. However, electrical chatter is when there's a change in contact resistance of that physical interface, and then it's often the result of vibration and can cause signal degradation or signal loss. When you have a mission-critical system, you could mitigate these losses via having redundant interconnects. However, we would prefer to avoid chatter overall. And the reason this is difficult is because there's no known relationship between the macroscopic vibrations that the interconnect feels and the microscopic electrical chatter. And this is a challenging thing to model for two main reasons. One, it's a multi-scale, meaning that we need to consider the interactions of the electrons for the electrical signal and millimeter-sized vibrations. In a similar field, where people are looking at the effects of friction at small scales, they end up having to consider the exact surface topography, which isn't always available and can be difficult to model. And we also have a multi-physics problem in that we have to consider mechanical, electrical, and the tribological surface interactions, which becomes computationally expensive. And even if we find ways to compute these factors, we need to find transfer functions, such as this R of x, to move our mechanical models into the same framework as an electrical model. Our approach to overcome these challenges is to start simple, using a single pin and receptacle system. And we'll start off with some analytical modeling of basic spring mass dampener representations of this system and an ODE solver, so that way we can develop some problem intuition. And then we'll move on to our data-rich experiments, in which we took simultaneous vibration, high-speed video, and resistance measurements in order to get the interactions of these different variables. For the analytical model, we decided to replicate the experimental system as closely as possible, and we represented the pin and receptacle as a collection of springs, masses, and dampeners, which could be then placed into ODE 45 in MATLAB and to get an analytical solution of the dynamics. In order to model the bending of the receptacle arms and the pin, we used Euler beam theory to extract a sort of spring constant, which could then be represented using our standard tools. The analytical model gave us some pretty good insight into how this system would respond to vibration. On the left, we're starting to see a chatter frequency. And chatter in this system is defined as when both the left and right arm are disconnected from the pin, preventing the flow of a signal. And what we see here is that as we change the frequency, the amount of chatter changes. And the system currently does a really good job at preventing chatter in a range from 1200 to 12,000 hertz. But outside of that range, it's very susceptible to signal loss. However, this modeling also can give us insight into how we could change the geometry to better reduce chatter. And we can see that as we increase arm thickness and moving to the right side of this plot, the chatter that results as high frequency is greatly decreased and nearly to zero. We also could model as if we encased this entire system in some sort of fluid. And we can see that the number of chatter events, or the amount of signal loss, decreases with increased viscosity of the fluid. And this can give us some better ideas of how we could design these pin and receptacle interconnects. Now, the data-rich experiments are going to be able to encapsulate more variables than we could come up with in an analytical model. So this is going to be the basis for what we really need to understand chatter. All of these experiments were performed last summer by the Nomad group at Sandia. They had a stationary pin and a receptacle that experienced vertical and horizontal vibration. They simultaneously measured the resistance at 40 megahertz and recorded every time that the resistance of this interconnect crossed 123 ohms. And they also took high-speed video at 10,000 hertz so we can use digital image correlation on the system. Digital image correlation uses the correlation between subsets of the image in sequential images to track objects over time. And using this, we can extract the full pin and receptacle dynamics. To perform the analysis, we use Sandia's Digital Image Correlation Engine, or DICE. DICE creates a numerical representation of the video by identifying subsets of the image, which is each of these blue dots, which track over time in the video. And with this numerical representation, we can perform Fourier transforms or displacement analysis to get the frequency contact or the chatter information from these videos. I'll now describe the analysis that was done on the 15 high-speed videos. To perform a Fourier transform, we first identify the 4 regions of interest: the receptacle body, the 2 arms, and the pin. And then we divide the subsets identified by DICE into their respective regions of interest. We can then take one of these regions and perform a Fourier analysis, which gives us the frequency content of its vibration. And for this case, the receptacle body, the top of the receptacle, was vibrating horizontally at 1040 Hz at a magnitude of 0.008 pixels, which, although it may seem small, can cause significant chatter in this system. We can also then look at how this vibration was transferred from the top of the receptacle to the pin where the contact was happening. And we can see that for some of the videos, we see very minimal transfer of vibration, but for other videos, the vibration in the pin, which is represented by these red bar charts, is much greater than the vibrations in the receptacle. And when we look at the reasons why, we can see that if the input vibration is sinusoidal, that the magnitude of vibration is greatly increased. And this is generally also associated with an increase in chatter. We can also look at the chatter of this from the high-speed video. And we do that by looking at the contact region and plotting the relative displacement of the right, left arms and the pin. And when the right and left arms are separated from the pin, we define that as chatter. And for this video, we predict that there's chatter occurring at 1 and 5 milliseconds. And we want to compare this with the work that was done from the 2019 electrical data to determine the effectiveness of using image correlation. The 2019 NOMAD group determined resistance by every time it crossed with 123 ohms and was recorded at 40 megahertz. So while this is not an apples-to-apples comparison, we should try and see a similar trend if we want to trust the high-speed video data. And we see some pretty encouraging results. That when we include the vibrations from the pin to the number of chatter events, it follows a very similar trend to the electrical data. This next plot specifically compares the number of chatter events recorded by the electrical system as by the high-speed video in DICE. And we normalize this by dividing by the number of samples taken during the video. And we can see that as the electrical chatter increases, the DICE chatter also increases, which helps us trust the high-speed video data, so when future analysis is done, we can be confident in the results. Project outlook and overview of what we've done. We've learned some really important lessons from a first pass on these high-speed videos. We think that we can trust the DICE chatter results, so we should also be able to trust other analysis that's done on the pin and receptacle dynamics. We've developed a framework that's general enough to work for other interconnect geometries. And moving forward, we still need to connect this information to modeling so we can transition to a design framework and improve the chatter resistance of electrical interconnects.